and this goes exactly the same way, right, that you would do in a 1D case, right. So all that you need is linearity, and instead of time invariance, you need what is called shift or space invariance. Okay, that's what we, okay, that's a word that's actually coined for an operation like this. So you can, so a discrete case, right, you can think of some, you see, delta mn, okay, which is which if you input to a let's say, you know, to an imaging system, and suppose you see an output which is, let's say, h of m comma n, and then I simply write this as, you know, 0 comma 0, just to indicate that it's an impulse applied at, you know, m equal to 0, n equal to 0. Now when I shift this impulse, right, let's say I do m minus n prime and then n minus n prime. So this is a Kronecker delta. Okay, this is not a Dirac. This is like a Kronecker delta. So it is like 1 at m equal to 0, n equal to 0, 0 elsewhere. So if you do this, right, then maybe, right, you can write this as mn, and then you can say that this probably depends upon where you apply it. Of course, for a shift invariant system it shouldn't matter, but in general it might matter, right. If you, it's not always true that if you shifted there. So that's why there is a difference between impulse response and you know, response to an impulse. It response to an impulse can vary. Okay, so when you say impulse response, that means you are actually indicating a convolution kind of, or an LTI system. Okay, and therefore, right, and then this just follows that, you know, if I have any, and why do you choose a delta? That is because any fmn, right, which is any image, you can simply write it in terms of, you know, this one in terms of the impulses as f of, you know, m prime comma n prime, and then delta m minus n prime, right, n minus n prime, right. I mean, that's how, so you can express any, I mean, that's how you do in your signals, right. If I gave you how do you express you know, a continuous signal, right. I mean, you will have an integral, then you will have impulse, right, I mean, shifted and scaled in terms of course the scaling is now coming in terms of the intensity f of m prime comma n prime. So you see that, you know, if you substitute m prime is equal to m and then n prime is equal to m, right, that's the only time when this guy is non-zero, and at that time you will get f of m comma n, right? So this is fine. But then what will happen is, right, when this kind of, when such a thing is being input, and if you assume linearity, right, if you say that my kind of system is linear, then it's like saying that, you know, I have one delta getting applied at m prime comma n prime, and you know, that is getting scaled, and then I have another. So what do we do in terms of a superposition kind of the principle? We say that, you know, if you have, say, f1 giving g1, f2 giving g2, then f1 plus f2 should give you g1 plus g2, and alpha m1 f1 should give you alpha g1, right, where alpha can be real or complex, whatever. So same thing, right? If you just apply that, then you know, this will simply turn out to be f of m prime comma n prime, and then this delta, right, will get replaced by h of m comma n, and then you have m prime comma n prime. Now on top of this, if you now assume space invariance or shift invariance, right, which is this LSI, right. So this is called LSI. Okay. So if you assume shift invariance, right, then what happens is, then this guy, right, is, you know, then what it means is, if delta mn went in and this came out, then delta m minus prime, m minus m prime, n minus m prime should simply lead you to f of m prime comma n prime, and then h of m minus m prime, you know, n minus n prime, and then simply 0 comma 0, because that should be exactly the same as what you had when you had delta mn. And therefore, right, the 0 comma 0 is no more information really, right. It just it makes no sense to, you know, carry it along. So you simply drop it, and you kind of, and you're back to this expression, right. So in a sense, what you're sort of saying is that when I kind of perform a filtering operation, the filter remains the same wherever I go. Okay, and that is one of the things that you are saying. And then the other thing is this kind of a linearity. That means if you have right, if you add, if you give multiple inputs, you know, at the same time, that is simply, you know, the output is just the summed outputs of what you would have gotten for, you know, for let's say each of those, you know, individual inputs. Okay, so this all follows exactly the same way, right, that you would do with respect to 1D. Okay, this is all you would have done in a 1D case. Just that, which notation? Oh, semicolon. That's just a semicolon. Just a semicolon. Oh, okay. This is just a semicolon to say that, right, there is still a functional dependence on m prime comma n prime. And when you assume shift invariance, you know, whether you have m comma n or m minus n prime, you still get 0 comma 0, and therefore there is no point taking it along, because I mean, it doesn't depend on that 0 comma 0 anymore. If it was dependent on m prime comma n prime, then you would have actually taken it forward, and no longer it has no significance, so you just throw it off, and that's why you get this h of m minus m prime comma n minus n prime. There's no point carrying it. I mean, we carried it initially because it could have been a function of m prime comma n prime. So it's like saying that, you know, if I applied an impulse, but today, right, and I see something, and then if I come back and apply an impulse, right, later, tomorrow, I mean, ideally I should get the same output that I got the previous day, but then shift it. But if that doesn't happen, then it means that it's a function of time, right, when you're applying. It's like your m prime comma n prime. But if it is not, then why carry that? Okay. Then now one interesting feature, right, that you will find, right, in terms of, and of course, this convolution is again the same thing, right, that I said. So if you had to flip, right, you would actually flip. Of course, now that we are into traditional filtering, right, so right, we should know what we do. For example, if I had something like f, right, and if my, let's say, origin was here, and now if let's say, right, this happens to be my filter or the image, and if I had to flip it around, right, then I could either, right, like I said the other day, you could either flip it about the y-axis initially, so in which case, right, it will come like this, and then, right, followed by flipping it with respect to the right x-axis. Well, right, something like that is what will happen. I mean, you'll first flip it this way, and then you'll kind of flip it this way, or you can flip it first itself like this. Okay, in which case, right, this guy would have become like this. If you had flipped it, okay, you would have gotten like this, and then right, if you had flipped it this way, right, then you would again be back to this, right. So whichever way you flip, okay, it shouldn't matter, but right, that's what you need to do. Just as in 1D you flip about the origin, here you have to flip about the two axis in order to get that m minus m prime, n minus n prime effect, and then you translate. Then, right, all of that is exactly identical. Right, slide this window all over the image, do a kind of weighted average. Okay, now one of the things, right, that is actually interesting is what is called separability. Okay, one of the notions that we have when you have a 2D filter is one of separability. So it's like saying that if I had a filter h of x y, then I mean, I'm going to be a little abusive here. I mean, sometimes I will write in terms of discrete, sometimes continuous. So please bear with me, because sometimes examples are easier to give in continuous when appropriate. So what it means is, right, if I can split this up into h1 of x into say h2 of y, right, that is when I say that I have a separable kind of filter, right, and this separability, especially, right, when you go to higher domains, because it has say various other implications, okay, which I don't have time to discuss about here. But in the spatial domain itself, right, there are certain implications in terms of the time taken to kind of perform the operation and so on, if it's convolution, especially in this case. So can you kind of tell me something, can you give me an example where you have a continuous function which is separable? XY? No, I mean, give me something more interesting. I mean, you're just saying x into y. This guy is like, no, give me something more interesting. No. E power? Okay. Well, no, but yeah, e power. But then something else that you have seen. Yeah, e power something that you have seen. Yeah, okay, yeah, so what I'm saying, there are so many of them which you have already seen. For example, a Gaussian is what I thought, I mean, right, that would be the first thing I thought you would say. What is a Gaussian? So if I write a h of xy, I mean, if you take the same sigma, right, then it is 1 by 2 pi sigma square e raised to power minus x square plus y square by 2 sigma square. This is what you are hinting at, but I mean, better to say that it's a kind of a Gaussian. I mean, why I'm saying is that these are the kind of things that are more common. I mean, right? For example, e raised to x square plus y square also is separable, but then that's not something that you often use, right? I mean, a Gaussian you've all seen, right? I mean, Gaussian is such an important function. Of course, see, if it turns out that your sigmas are not the same, then you will get like 1 by root 2 pi sigma 1 e raised to minus x square by 2 sigma 1 square into whatever 1 by root 2 pi sigma 2 e raised to power minus y square by 2 sigma 2 square, right? But if it is the same sigma, then right, this is what you get, and of course, right, this automatically splits, as you can see. And then what other functions? Gaussian then e raised to power. I mean, right, if you have this case, right, 2 pi by n, right, if you have a DFT, right, what will you have? 2 pi by n mk plus let's say, right, nl. I mean, if you had a 1D DFT, it will be 2 pi by n kn, right? This is what you have. If you wanted a separable 2D, right, that's what it will be, e raised to power j 2 pi by n. Similarly, a continuous case, right? You can. So right, these are actually things that you have already seen, and there is something else which is special about a Gaussian, which is not so special about the other thing that we have written. What is that? let's just see, right, how much attention you guys must have paid, right, during the filtering or signal processing course. A Gaussian is something even more special. Of course, separable and all that is okay. That the other guy is also there. What else is there very special about a Gaussian? Its Fourier transform is also a Gaussian, right? What is the Fourier transform of E j omega naught t? Some shifted version. Dirac. Yeah, it should be a delta. Dirac delta, right? I thought you said shifted version of itself. Oh, shifted version of delta. Okay, I heard it as shifted version of itself. That's what I was wondering. Where did that come from? Okay. So, but then, so in that sense, right, I mean, the functional form suddenly changes, right? And normally that's the case. But there are special signals like a Gaussian, right, where when you take the Fourier transform, it still kind of retains its shape. Anything else that retains its shape? We talked about impulses, no? Can you think of something with respect to an impulse that retains its shape? In the sense that you take the Fourier domain, retains the shape. Gaussian retains. What is the Fourier transform of this Gaussian? No, I know, but what is the form? E raised to power minus omega square plus nu square by 2 into sigma square. Sigma square goes on top. Right? That is a 2D Gaussian Fourier transform. Fourier transform of this guy with this normalization factor thrown in. What is the importance of this 1 by 2 by sigma square? Yeah, exactly. If you take the area under this curve, it's 1, right? And therefore, G of 0 should be 1 here, right? Because G of 0 is like the area under the curve, right? So, okay, that should be 1. And so Anirudh, give me one signal other than a Gaussian which retains its shape. Exactly, right? Impulse train. An impulse train is again an impulse train, right? In the Fourier domain, and then now already you can talk about combinations of Gaussian with impulse and all that, right? You can get so many signals like that whose Fourier transform and all this. Okay, now the point, right, to actually note is that when you have a separability like that, right, what it means is, it actually makes life a little simpler. See, for example, I mean, if I had an image, right, and suppose I had a let's say, M cross M filter. Okay, I have an M cross M filter, and this image is actually N cross N, right? And now when I want to do a convolution, I'll have to, of course, take this filter, apply it, slide it everywhere, right? So if I just remain at, even if I stay at one place, right, there is at least m square multiplications that I have to do. Then I have to do maybe m square minus 1 additions and so on. Let's just look at the multiplications, right? Now at one pixel I have to do m square multiplications, and there are n square locations like that, right? So I'm looking at even in the simplest case, right, if I just look at the multiplications, looks like I need to do m square into n square multiplication. Is that correct? Right? M square into n square multiplications. Now, if you had a separable filter, right, then what happens is equivalently, right, what you can do is you can take this by a separable filter, right, what you really mean is something like this, a one dimensional filter multiplying another is a 1D filter. That is the right, there's an equivalence of this. So for example, I mean, let me give you an example, right? If I had, let me ask you, right? Suppose I had 1, 2, 1, 0, 0, 0, minus 1, minus 2, minus 1. This is a separable filter. How would you separate it?
1 to 1.
1 to 1, 1, 0, minus 1, right? So you see that this is a separable filter. And 2, 0, minus 2, right. So 1, 2, 1, 1, 0, minus 1, right. Now the good thing about this is that you can get the equivalent effect. Whatever you got through the 2D filter, which you did here, you will get exactly the same effect if you were to first do a convolution. Let's say, if you try to do a vertical filter, a 1D filter, if you applied on this image vertical, so the first filter, if you took it, if you had to apply the convolution, finish it, and then you apply a horizontal filter. Right, you will get the same effect, okay, whatever you got with this filter that you applied like overall. But then in terms of computations, now if you take this filter, right, this has how many entries? What is its size? M cross 1, right? So the size is m cross 1, and therefore in terms of the multiplication, how many multiplications do you need now? M into n square. M into n square, and so it's like 2m square, right? So that's all you need. Whereas there you needed n square by m square n square. So you're looking like m square n square by say 2m n square. So the gain is what is this? M by 2, right? and if m is reasonably large, so you can already see that that it makes a lot more sense. So separable filters, right, people kind of look out for, okay, and even in the oh, you'll have more additions. Why do you have more additions? I mean, there also you had like m square minus 1 additions. Here you will have like 2m minus 1 additions, right? It won't be more. Okay, but the separability, of course, this is like one way to look at separability, but it has lot of implications in terms of if you do Fourier analysis at all, which we are not kind of going into. Okay, but just right, I just wanted to say that even this convolution operation when you are doing, you should remember that if you had a separable filter, then right, things can be easier. Then among the filters, right, that are most commonly used, right, I'll just talk about two of them. Okay, one is called a box filter. Okay, these are all handcrafted, right? I mean, unlike the ones that you saw with respect to CN and so on. These are all handcrafted guys. So in a box filter, it's like, or we call it a uniform filter. Okay, so it looks like, I mean, if you had 3 cross 3, then you will have like 1 by 9, and then right, all ones. Oh, 3 cross 3. I think I had to draw it properly. 1 by 9, all ones inside, so that it sums to 1. And there is actually a reason, right, why I mean, there is a physical reason for this, why this average and all should sum to 1. In the simplest way to kind of think about it is, you don't want, so an averager when you apply, right, nowhere, right, will you, what to say, I mean, okay, I mean, this has to do with energy conservation so on. I mean, there is something to do with optics and all that. When you have a lens cannot inject energy and so on. So the box filter, we'll just use it as an averager, right? We just want to smooth things. If you want, whenever we want to smooth, right, we'll use an averager. And similarly, if you wanted, a difference operation, right, then right, I mean, you can kind of think of filters of whatever kind. The simplest, right, could be whatever, right, 1 1 1 1, and then you see, right, minus 1 minus 1 minus 1, or the one and then 0 0 0, right, in the middle. So you can think of, and of course, then depending upon the orientation, right, I mean, then you may, so for example, right, if you had an image, okay, where let's say you have 255 intensities here, and then you've got like 0 here. That's a very sharp edge, right, that you have here. Okay, here is where the transition happens. Then if you have to pick up a vertical edge like that, right, then see, the other filter that you could have is for a horizontal edge, right, which you could maybe write like this. Okay, so if you wanted a vertical edge, right, you would probably, right, go for that filter. If you wanted a horizontal edge, something like this, right, you would have to go for a filter like that. Let's say this is 255 and this is 0. And the other thing, right, that you will typically find is that sometimes, right, okay, this will have like, the other one that I showed, right, this is actually a standard filter, 1 2 1, this is called Sobel, 0 0 0 1 minus 2, minus 1 minus 2 minus 1. So you see that, right, there is an extra 2 that comes in there, that is to actually weight, I mean, so for example, right, I mean, that is to give more weighting to the central pixel. We can see that, okay, when we actually do it. I mean, I'll show that. But the other thing that you actually notice is that, why do you think they do this 1 2 1 and minus 1 minus 2? Why don't they just do this 2 0 minus 2? I don't know, or 1 0 minus. Okay, if you want some weightage, let's say that. Why do they do that? Why do they have like, why can't they be happy with just a, of course, in this case, right, we showed that, right, doing this is equivalent to, multiplying with those two filters. But I'm saying, generally, right, when you have like 1 2 1 and then minus 1 minus, what do you think could be the reason? Okay, so what exactly are you doing to counter noise? You are averaging, right? You are averaging in a sort of a direction along the edge. Right, you see this, no? So right, what you are doing is you are sort of adding up intensities, right, along the. So if you are looking at a vertical edge, it's okay to average along the edge. I mean, you should never average orthogonal to the edge. I mean, then you'll end up smearing the edge. But it's actually perfectly okay to go along the orientation of the edge and do an averaging, because that will counter noise. right? I mean, if you had noise, then we all know that averaging actually reduces, provided the noise is independent and so on, it reduces the standard deviation of the noise, right, depending upon how many you average. So that is the reason why you have this. Typically you will have like some averaging going along in this direction along the edge, and then a differencing that goes on in a direction which is across the edge, right, orthogonal to the edge. So it's the same thing, right? You could also have for a horizontal filter. Now, so in a sense, right? So a difference is like a gradient filter. Okay, so in a sense, right? We will call these as gradient filters, and this we will call as an averager. Okay, and I'll just show you a few examples just to right, pick your mind on right, what those things may look like. Okay, if you just so right, this is like a small little okay, this and all we'll skip. Okay, this is how you know what to do. Okay, now think about this, right? So I have a bunch of filters, right, which I'm going to apply on this image on the left, right, and then you have to tell me what is the kind of output I'll get. Okay, so if I actually convolve with a 2D filter like that, what will I get as output? Identical, right? I'll get the same. Okay, so it's unchanged. What about this? Sobel, right? So what do you see here? I mean, what kind of edges have emerged? Edges have come, but what are those edges more like? They are more prominent, vertical or more prominent, right? Here, horizontals are more prominent. Now we can see the eyebrow, this one, right? What is that? Forehead, lines, streaks, mustache. What about this? Sharpen. No, the right guy is a blur, but then now you are subtracting the original from the blur, right? So it should sharpen. Oh, was the answer already there? No. Okay. Good. Okay. Right. So now the point is right. So okay, I think there are a few more examples. Okay. Fine. Now one of the other filters, right? 1 minute. I think there are a few more examples that could be interesting. Okay, or else we'll first finish this and then we'll come to that.